Well, welcome back, everybody. Like we are now at the halfway mark, so we got a bit to go. Okay. Well, what I want to do today is you may have noticed that first of all, in the next exam, I have moved it. So today I want to finish up 7 and 8. Get 7 and start 8. Finish that on Thursday, and I moved it. I believe Friday is the exam. I'll double check that. If not, it will be Friday. I moved it to Friday. I want to make sure I get done with the chapter 8, and then we'll continue. So obviously, all the other all the other exams are going to be moved forward accordingly. It's been kind of tough scheduling for summer, given we've got 8 weeks normally, as I mentioned before. In fact, one thing I removed is activities on top of this during the regular semesters. We had an activity that does multiple different things. I removed that, given the time constraints and so forth. So anyway, let me let some more people in here. Let me continue with 7. We're about almost done with it. One other thing. I did have Cox come out. They checked the cable. They give me a new modem. Let's see. Let's hope for the best here. Okay, so hopefully it won't cause me to crash here with my internet connection. Okay. There's a question. All right. Okay. Chapter 7. Let me share the screen. And we were talking about beginning to talk about bonds, polar bonds and non-polar bonds with respect to covalent bonds. Remember, ionic bonds is a combination of a metal and a non-metal. That's important. You got to get that concept. A metal and a non-metal. And you forget what a metal is, then there's a slide where we talked about this, about who are the metals and who are the non-metals. Okay, you can use the periodic table to help you out, because the periodic table, there's a little stair step. On that stair step are the metalloids. Those are the elements that have properties of metals and properties of non-metals. To the left of that stair step are all the metals. Okay, excluding hydrogen, because hydrogen's on the left-hand side. And so all those metals in a combination with a non-metal. And who are the non-metals? Those are the guys on the right-hand side of that stair step. Things like oxygen, things like fluorine, chlorine, bromine, nitrogen, phosphorus, sulfur. When those two get together to form a compound, that is an ionic bond. It's really not a true bond, because what's happening, the metals lose electrons. Remember that? Put that in long-term memory. Non-metals gain electrons. So we have a full-fledged positive and a full-fledged negative charge, and they attract to each other. So there's no sharing of bonds like in covalent compounds. Covalent compounds are when there's more than when more than two non-metals get together. Okay, now within the covalent category, there's only 2 categories, ionic and covalent. Under the covalent category, there's 2 types of covalent bonds, polar, non-polar. Basically, non-polar is equal sharing of those electrons. Unlike the ionic bonds, where they have a full-fledged negative positive charge, there isn't a full-fledged negative and positive charge in covalent bonds. Those electrons are being shared in that bond. When there's equal sharing, okay, I repeat, when there's equal sharing of those electrons, because the electronegativity, here we go, electronegativity, and that is the affinity to pull electrons onto themselves. When they're the same value, then they get equal sharing, we end up with a non-polar bond. Okay, so all of the diatomic compounds have a non-polar bond. The other one that has a nonpolar bond is a carbon hydrogen. Now, I was asked the question, why is that? That is because the electronegativity of carbon and hydrogen is so similar, they're essentially the same. And it's treated as like the diatomic bond. They're equally the same, so the tug of war is equal. So carbon hydrogen bonds are nonpolar, all the diatomic bonds are nonpolar. Okay. When there is unequal sharing, okay, here we go again. When there is unequal sharing, what do I mean by that? Because when there's two nonmetals that are bonded and one of them has a higher electronegativity than the other, you have unequal sharing, resulting in one of the atoms pulling the electrons onto themselves much greater than the other one that is bonded to, the other atom is bonded to, resulting in a partial negative area and a partial positive area. Not a full-fledged charge, but a partial, okay? And that is a polar bond, okay? We need to grasp that concept. Why? Because that's going to tell us that affects the properties of the molecule, which then allows us to determine certain forces that occur depending on the type of bond, which then allow us to predict such things like whether it's soluble in water or not, whether compare and contrast the boiling point, the melting point, okay? And that's down the road. So if you have a tough time with the polarity, this is where you got to grasp it before we can move on and really talk about what we're going to talk about eventually, called electromagnetic forces, IMF forces interacting. But they're all tied into polarity. And polarity keeps coming over and over and over again, okay? So bonds, and the thing is that if you just look at the bond and you see that you have two different atoms, that's the thing, the whole premise of this polar bond. If there are two different atoms, remember exception, carbon, hydrogen. If there's two different atoms bonded together, it's polar automatically. You don't even have to think about it. So the examples are carbon, hydrogen bond, polar. You know, hydrogen chloride bond, polar, okay? So on and so forth. Couple of questions. Mason had a question. Do metalloids act like, when they are paired with metals, depending on what they are, they can, like silicon can act like, carbon hydrogen bond. Silicon can bond with hydrogen to form silicon compounds. And there's some metallic properties to it. It's very important because we do know that a lot of our computer chips are silicon based. So they do conduct electricity to a certain amount. Okay. Aaliyah had a question. For example, the bond is CH3Br. Would you compare the electronegativity of carbon, hydrogen, and bromine to determine if it's polar or nonpolar? In this scenario, CH_Br, that means carbon's a central atom. We go through the Lewis dot structure, and you end up with a tetrahedral position. Okay, tetrahedral for CH_Br. Now, carbon, hydrogen, that particular example, which is a good example, those three bonds are nonpolar. Now, if they had four carbon hydrogen bonds, just by default, they would be nonpolar. But the fact that there is one carbon bromide bond, which is a polar bond, tells you end up the result is the overall effect for that example that Aaliyah put in would be a polar molecule. It will have three nonpolar bonds and one polar bond. Now, if you run through the exercise and now replace another hydrogen with a bromide, and now you got CH2Br2, two polar bonds, two nonpolar, overall polar. Continue that exercise, go all the way around and replace all of the hydrogens with bromides. Now you have 4 carbon bromide bonds, okay, which by default are polar, but because of the geometry, the tetrahedral geometry and the symmetry, those 4 polar bonds cancel out. So even though now they got 4 polar bonds, they cancel out, and overall the molecule is nonpolar. Okay. So in between, as you start off with carbon, 4 hydrogens, all nonpolar bonds, nonpolar molecule. Replace 1 hydrogen with a bromide, bam, I got a polar molecule. Replace the next one. We replace 3 of them with bromides all the way around. You got a polar molecule until such time that you replace all 4 again. And now you go back to a nonpolar molecule simply because the geometry of the tetrahedral position cancels, those 4 bonds get canceled out. Okay. All right. What do I got here? All right, something. All right, so as I was stating here, let me share my screen somehow. So all these examples are carbon, oxygen, hydrogen, chloride, sulfur, fluoride, silicon, and nitrogen. All are polar covalent bonds. First of all, why they're polar? Again, I can't overemphasize. 2 different atoms, okay? They automatically have 2 different electronegativity values, which results in one of these pulling the molecule closer onto itself, which results in a polar bond, meaning on one side we have got a partial positive and the other side we have a partial negative side. We're going to learn which direction this pull goes to in here in a second. Okay. And what we do is we use this arrow. It houses the direction of the polarity. That symbol written up here is the lowercase Greek symbol for delta. Right in here, right there. Delta, meaning partially positive or partially negative. There is a pole, not a total pole. We don't have a full fledged charge on it. Okay. Now we're using arrow to demonstrate in which direction the polarity, the pull is going to. And that is all simply dependent on which of the 2 atoms has a higher electronegativity. You might say, do I have to learn all of the electronegativity values for each atom? No, you don't. You want to, you go right ahead. Every element has a electronegative value, exception of the noble gases, and but we don't have to, because what we do know is this: that fluorine is the most electronegative element there. So that is our reference point. Okay, so and the train goes from left to right toward fluorine, the electronegativity increases. Let me pull it up here. Okay, so we got fluorine sitting right there. All right, so the electronegativity trend from left to right increases, okay, and from bottom to top increases. And we use the fluorine as our reference point. So we want to compare the electronegativity of, say, 2 values, okay? All we got to do is find its position relative to fluorine. So let's compare a carbon and a hydrogen bond. So we find carbon right here, we find a nitrogen bond. So we got a carbon nitrogen bond, and we need to determine who's more electronegative. Well, we simply find the position relative to fluorine. We see that fluorine is a lot closer, nitrogen is a lot closer to fluorine. Therefore, nitrogen in this example of a carbon nitrogen bond is the most electronegative element of the two. Therefore, the arrow goes from carbon to nitrogen. So we can draw an arrow in that direction, which tells us that the nitrogen has a partial negative side and the carbon has a partial positive side, because the nitrogen having a higher electronegativity is pulling those electrons more. So it's a tug of war, and nitrogen is winning that tug of war and it's pulling more of that rope, if you will, more of the electrons onto itself. So we end up with a dipole bond, a permanent dipole bond. That is the nature of the beast of a carbon-nitrogen bond. It's permanent dipole. Okay, that's as compared to later on, we're going to learn about temporary dipoles. Is boron a +3 ion? Yes, boron can be a +3 ion. Okay, because if it's going to lose electrons, it's going to lose those 3 electrons. But it's a special case because it is a metalloid, and being a metal, it can also act as a non-metal versus a metal. Okay, because boron's right on the stair step. Remember, on the stair step are the metalloids, which means they're going to have metal properties and non-metal properties. Like boron has, there's a whole science that could be a whole class unto itself, boron and the molecules it makes. Very interesting compound, or element, I should say. And it makes some very interesting compounds. So back to our narrow. So if we look at carbon fluoride, we know that the fluoride is, without even question, is the most electronegative element there. So the arrow goes from carbon to fluoride, with the partial negative on top on the fluoride and the partial positive on the carbon. This polarity is very crucial when it comes to chemistry and making compounds, because when something is very nonpolar and doesn't have a polar bond, it is difficult to run reactions to create something from something that doesn't have a polar bond. As a chemist, as we make new molecules and make new things, the very first thing we look at is we look for areas that have a polar area, because that allows us to do chemistry on that area. Doing something that doesn't have a polar area, not that it's not doable, but it requires special conditions like catalyst and maybe even such things as metal catalyst, and very, very difficult to get something to happen chemically. Okay, so we look at oxygen and hydrogen. What does that tell you? All OH is on a molecule, polar bond. The arrow goes from hydrogen to oxygen. So the partial negative is on the oxygen. And then we got a bond with the phosphorus and chloride. Again, find this position. We see that the chloride is a lot more electronegative than the phosphorus. You might think, oh, wait a minute, phosphorus, you know, think about it. The chloride's right underneath the fluoride. It's on the periodic table. It's touching fluoride, if you will, on the periodic table. So it's a lot more electronegative. So the arrow goes from left to right in this scenario, with the chloride being a lot more electronegative. Okay, so polarity, very important concept with respect to chemistry. It has a vast effect on chemicals. Down the road, we'll learn more about it. Of course, we know that noble gases don't have an electronegative value simply because their octet is fulfilled. That happy 8 has been fulfilled. There's no drive for it to do anything, okay, chemically. Now, as a side note, and I repeat, as a side note, when we get down the periodic table into the big, gigantic noble gases, there's a little bit of reactivity there, but it's a totally different reason. Okay, so all right. So if you're given something like this, and you're given a bond of 2 different elements, the first thing you notice that, okay, carbon, hydrogen, 2 different elements, polar bond. Okay, Question now, which direction? From carbon to oxygen, oxygen to carbon. So we find this position relative to fluorine. We see that oxygen is a lot more electronegative. Therefore, the arrow goes from left to right, from carbon to oxygen, and meaning the partial negative is on the oxygen. Now, on the course website, when I talked about this, there is under the additional resources, a simulation to help you understand this. I ran to it last time. As far as the polarity, you can see by the color change of how one, as the electronegativity changes in one of the elements, it tends to pull the electrons onto itself. So you might use that to help you out again with this particular concept. Nitrogen fluoride, no question, fluoride is the most electronegative. The arrow goes to the fluoride, giving it a partial negative on the fluoride. Oxygen to hydrogen, we did that. Oxygen is a lot more electronegative, so in this case, the arrow goes from right to left. Now, occasionally, it could be written HO, okay? Don't let this confuse you. And the direction that the arrow goes is depending on how they present the bond. So it could be written hydrogen to oxygen. Okay, no big deal. So we draw the arrow to oxygen with the arrow on the oxygen and the plus side on the hydrogen. So you got the partial negative on oxygen, partial positive on that. That's the same as this. Just take this image and just flip it over and you get the same thing, okay? So be aware how they wrote it for the assignment, and that way it assures you that you're sending the arrow in the right direction. Chloride to carbon, okay? Chloride, beyond no question, is a lot more electronegative, so the arrow goes from right to left, partial negative on the chloride. And then what can you say about the carbon hydrogen? Where's the arrow go? Which direction? Exactly. No direction, again, because even though it's two different elements, hydrogen and carbon, you might want to think, okay, two different elements, and that 99% of the time that it gives you the right answer. But when it comes to carbon and hydrogen only, the electronegativity of those two are essentially the same, resulting in a nonpolar bond. And being nonpolar, there's no arrow, no partial, because the bond, the electrons are equally shared. Okay, exactly, guys. All right, so the question here says, are these bonds ionic, or are they polar covalent, or polar nonpolar covalent? Okay, well, to answer ionic, the very first thing you need to know is, how do we define ionic? Again, it is a metal versus non-metal. If we look at bromine and bromine, what do we have here? Could it be ionic? It can't, right? Because they're both bromines. And we know bromines, if you find them in the position on the periodic table, they're on the right side of the stair step, okay? Being on the right side of the stair step, they are non-metals. So therefore, we have a covalent bond. Now the next question is, are they polar or non-polar? The fact that they're the same tells you that they are non-polar. All right. If we look at phosphorus and fluoride, again, non-polar elements giving us covalent bonds, different elements telling us that it is polar, okay? Sodium and chloride, good old table saw. Obviously, we have an ionic bond here. Why? Because sodium is a metal. Sodium is in group 1, okay? Way far left of the stair step. It is a metal, and chloride is a non-metal. So by definition, it is defined as a ionic bond, or ionic molecule, if you will. And the last one, we have a diatomic. You might think, oh, wait a minute. It's diatomic, two halogens. However, they're different, right? The fluorine and the bromine. Okay, two different elements. So automatically polar, beyond being polar, we know we have to draw arrows here, that arrow would definitely, let me draw it. So there'll be no arrow for bromine, but it'll be an arrow for the phosphorus and the fluoride. It'll be from left to right. So there'll be partial negative on the fluoride, partial positive on the phosphorus. None on the sodium chloride, okay? And on the fluoride, and the way it's written, it'll be from right to left, okay? With a partial negative on the fluoride, partial positive on the bromide, if arrows needed to be written. Okay, so polarity, it's going to pop up more again and again and again throughout the semester. So it's really, you really need to grasp this. It's really going to be important with respect to down the road with respect to the other chapters. Just think of it as a tug of war of bonded electrons. Essentially what it is. We got a tug of war. And when the electronegativity is either the same or extremely very close, you know, we have a nonpolar, we have an equal pulling of that bond, equal pull of those electrons. Okay. And therefore we have a nonpolar bond. If the bond is unequal with respect to the electronegativity, we end up with a polar bond. Okay. Except, as we stated, the carbon hydrogen. And so we can look at this here. We got the question is ionic, polar, nonpolar. All right, well, we can very quickly run through this. And, you know, the first thing says ionic. Okay, so that's a combination of a metal and a nonmetal. So we can look through this list here and very quickly highlight the metal and nonmetal. So we got sodium chloride, we just did that. Hydrogen chloride, we got two nonmetals, H and H, two nonmetals, chlorine and carbon, nonmetals, carbon and hydrogen, nonmetals, oxygen and oxygen, nonmetals, potassium and oxygen. Okay, and so that is a ionic compound. Okay, and then we got a phosphorus and a fluoride. Let me clear this up, got messed up here a little bit. And so the ionic bonds are circled in yellow color, okay? Because that is a combination of a metal and a nonmetal. That means that everyone else must be covalent. The question is it polar or nonpolar? Okay, so we look at hydrogen and chloride. Again, hydrogen nonpolar, chloride nonpolar. We definitely have a covalent bond. Question is which is a polar or nonpolar? Well, there is a difference in polarity here because of electronegativity. Hydrogen is way far left on the periodic table compared to where chloride is compared to fluoride. So without question, it's very different as far as the electronegativity. And we can draw an arrow from left to right, okay? And so we have a polar covalent bond with a partial negative on the chloride and a partial positive on the hydrogen. That difference here, okay, here's an important concept to remember. Ionic bonds, ionic compounds, when we place them in water, will dissociate, they break up. Think of it as I got two magnets here, okay? Two magnets sitting right here. So I got an ionic bond, they come together, they attract each other, and that's the electrostatic attraction. Now, when I place them in water, again, ionic compounds, when I place them in water, they completely break apart and they dissociate. So now I get the two ions separated. Now, the ionic compounds all do that. Now, some of them do this 100% dissociation. Some of them dissociate not so much. But the point is, all of them, all ionic compounds will dissociate completely into the ions or partially. They will dissociate. Covalent compounds, when you place them in water, they do not dissociate. Or I say water, but any other solvent they're soluble in. They do not break apart because that bond is a permanent bond there, okay? So covalent compounds do not break apart into ions. That's important. The only exception is acids. We have a whole chapter on acids. And those hydrogen, HCl is an acid. An acid is a covalent compound that when put in water will dissociate. And it dissociates because even though they're not ionic, the electronegativity of the two is so different, I should say, value-wise, that the hydrogen and the chloride dissociate to form an acid, or we call proton. But that's the only exception. Covalent acids, organic compounds, will dissociate like the ionic compounds. And also like the ionic compounds, some acids dissociate 100% and some dissociate much less than 100%. But more on that down the road. Okay. The next one we have, so we have here a polar covalent bond, polar bond for HCl. Hydrogen and hydrogen, okay? The elements are the same, okay? It's diatomic, and so we got nonpolar, NP. Chloride and carbon, okay? Two dissimilar atoms, we have a polar bond. Polar bond for carbon, chloride, and carbon. All right, carbon, hydrogen, as we spoke of earlier, this is nonpolar. All carbon hydrogen bonds are nonpolar. Oxygen, O2, the oxygen, there's a double bond in oxygen. That's what that equal sound. Equal represents a double bond with two oxygen atoms. Oxygen is diatomic, okay? Two elements that are the same. So we have a nonpolar species. The one in yellow, as we talked about, it's ionic compound. And the phosphorus fluoride, two different ones with two different elements, we have a polar bond. Okay, polar bond. And let me use this. So ionic for that one, polar covalent for HCl, good old HCl. That is the formula from that acid in your stomach, by the way, HCl. HH is a nonpolar covalent. Carbon and the chloride, it is a polar covalent bond. Okay, now we're just talking about the bonds here. Okay, we're not talking about for the overall molecule, whether it's polar or nonpolar, because as I mentioned earlier, you know, if you have, I'll come back to that in a second. Let's finish the list here. Carbon, hydrogen, nonpolar bond. Diatomic oxygen, nonpolar covalent. And we have an ionic compound for potassium and phosphorus and fluoride, we have polar bonds. Okay. Now, earlier, maybe now I can draw it a little bit better. The question was asked about a carbon. We can use chloride or bromide. So we had CH3, we can use chloride. And so structurally, we have, let's put hydrogen there, and then bringing out that wedge, trying to draw a three-dimensional image in a two-dimensional world. Okay, so we have a polar bond here, carbon chloride, but overall the molecule is polar. We got 3 nonpolar bonds and 1 polar bond. Okay, so we got 3 nonpolar bonds and 1 polar bond, PB, polar bond. So overall, this molecule is polar because of the 1 polar bond. Now, if we go here and replace one of these hydrogens with a chloride, now we have 2 nonpolar bonds and 2 polar bonds. The net is still polar molecule. We go around the horn and replace another hydrogen with chloride. Now we have 1 nonpolar bond and 3 polar bonds. We still have a polar molecule, okay? Because of this 1 nonpolar bond, overall, the 3 polars overpower the nonpolar. Then finally, we replace the last hydrogen with a chloride, this carbon tetrachloride, for example. So now we have 0 nonpolar bonds and 4 polar bonds. And you would think, okay, I got 4 polar bonds. Now the molecule is definitely going to be is polar overall. However, because of the geometry and tetrahedral position, those 4 polar bonds cancel each other out. And by canceling each other out, we end up with the overall non-polar molecule. Okay. When a molecule has non-polar bonds, overall 100%, okay, 99.999%, because nothing's 100%. Non-polar bonds, overall non-polar molecule. When a molecule has polar bonds, generally it is a polar molecule unless the polar bonds cancel out. Another example is carbon dioxide. We did that example, but a refresher. Carbon dioxide had 2 double bonds, but we had 2 polar bonds. Now, this carbon hydrogen is a polar bond, and this carbon hydrogen going the opposite direction is a polar bond. Okay, there's a polarity. We've got a partial negative over here, partial negative over here, and 2 partial positives due from each one. But because those 2 arrows go in opposite direction, they cancel each other out. So carbon dioxide is a non-polar molecule, even though it has polar bonds, okay? Because the polar bonds canceled out. All right, so this is what I rehashed of what I just explained. When all the bonds in your molecule are polar, non-polar, you end up with a non-polar molecule. If the polar bonds do not cancel out, like in this example, sulfur dioxide, you have a polar molecule because the arrow, look at the arrow, so there's a dipole between the sulfur and the oxygen in both directions, except because of the geometry, okay? Because of the geometry, those double bonds do not cancel out, okay? The general formula, we have to do the Lewis dot structure, and you end up with A, B, 2, E. That's the general formula. You got that lone pair on the central atom sitting right here, which means that this bond that you would think maybe it's like carbon dioxide, example, like that, because of the lone pair, there's that angle gets squished where it's not 100. You would think it to be 120, like if you do the geometry, let's say, oh, well, anyway, you see that there's lone pairs and that bond angle puts that sulfur oxygen bond in the position that they don't cancel each other out like in carbon dioxide. In carbon dioxide, those arrows cancel out because they're going in opposite directions. Okay, give me 1 second. 1 second. Okay, I'm back. And so if the polar bonds, in essence, if the polar bonds cancel each other out due to the geometry of the molecule, and how do we get the geometry of the molecule? We use the Lewis dot structure process that we utilized before to get the geometry, which gives us the general formula, AB2E is the case there, which gives us that geometry. And so we can see that the sulfur oxygen bonds cancel out. Okay. And this one, the next one, carbon dioxide, had the general formula of AB2, which is linear. And there's the geometry written there in the diagram. And the arrows, remember these arrows are what are called mathematically called vectors. Basically just means that they have direction and magnitude, and those arrows represent the same magnitude. So one of them goes to the right in the positive direction, and the other one goes to the left in the negative direction. And the result is they cancel each other out. Okay, and that results in a non-polar molecule, even though that they have polar bonds. Okay. All right. So, methane, carbon, and 4 hydrogens. The fact that we do the geometry, this is it should be tetrahedral. There's 4 carbon is the central atom. There's 4 hydrogens bonded around it. Tetrahedral. The formula, general formula is AB4. Okay, they're all nonpolar. You end up with a nonpolar molecule. Okay. Now PF3, if you go and do, and I'll leave this part to you so you can get some experience with respect to Lewis dot structures. But after you're done, you should end up with a structure geometry that looks like this. Counting all your valence electrons, it should look something like this with a lone pair on that central atom. And the general formula would be A, B, 3, E. Okay. The fact that you've got a lone pair in the central atom, automatically, as a rule of thumb, you have a polar species. Okay. Okay. And then carbon dioxide, we talked at length about that, you know, because of the direction of the polar bonds of the carbon oxygen bonds, they cancel each other out. So we end up with a non-polar species. You see, and what this does is we kind of use this as we use water and oil. Okay, so when we talk about something that's polar, we're going to take it and say, okay, it's polar, so I would predict that this molecule will be a lot more soluble in water than this molecule. So for example, methane being all nonpolar and keeping in mind that like dissolves like. Things that show similar, hold on 1 second. The mouse is going crazy here. Polar solvents will dissolve polar molecules. Okay. Nonpolar solvents will dissolve nonpolar molecules. So we can make a prediction here with carbon dioxide. Carbon dioxide is shown to be a nonpolar molecule. So therefore, it would exhibit more solubility in nonpolar solvent than would in polar solvent. Okay. And PFCl3 being polar would exhibit more solubility in polar solvents than in nonpolar solvents, simply because of the polarity. Now, Claudia had a question. Does the term dissociate equate to solubility? Not necessarily, because we have a good example would be sugar. Solubility is just the ability of a molecule, be it polar or nonpolar, to dissolve in a solution. And we know that sugar dissolves. That's why you got sweet tea, right? Okay. However, sugar is a covalent compound and it does not dissociate. So dissociating means it breaks apart into their respective ions. We know that sodium chloride is ionic and it is soluble in water. We can make salt water or brine water, right? We can take some table salt and we put it into the water and it will actually break apart to form the ions. Now, which means this, if we had a tool called the conductivity measure, we can measure the conductivity of a solution. If you take pure 100% water, it does not conduct electricity. 100% water, pure water, will not conduct electricity. You could take a bath with 100% clear water for a few minutes and throw your hair dryer in the tub and you'll be okay, but don't do that at home, okay? Why? Because there's no ions in the solution to carry the current. So 100% water has no ions, okay? The moment we put these ions in solution, it will conduct electricity. So ionic compounds, be it 100% soluble or not so 100% soluble, when they go into water, they dissociate. They break apart into the ions, okay? And hence they are soluble, but they conduct electricity. And we're gonna have a whole chapter on this. Sugar is soluble, but once we dissolve it, it will not conduct electricity because it doesn't form ions. Okay, so the two terms are a little bit different. All right, so you might want to try this. We did the water, we did ammonia in the previous chapter, so we don't really have to do it. But if you might want to do it for practice again, get the structure and then determine whether it's polar, non-polar. You know, we use water as a reference point with polar solvents. So automatically, you know that water is polar, okay? And if you think about the last one, ammonia, which we did, it's got a lone pair on that central atom. In fact, everybody in group 5, nitrogen and phosphorus, will have a lone pair on the central atom. And group 6, like oxygen, will generally have 2 lone pair on the central atom. And group 7 will have 3 lone pair, but I'll introduce that information down the road here in a bit. All right, so try those at home. And that ends chapter 7. Okay. Which brings me to chapter 8. Any questions on chapter 7 at this point? Okay. All right, well, nomenclature. Yeah, a couple of questions. Oh, to determine the question is, will be asked to determine the molecule's polarity to get, yes. Because they're going to ask you, you know, you could get questions like, all right, here's the formula. What is the Lewis dot structure? From the Lewis dot structure, determine the geometry and then determine whether the molecule is polar or non-polar based on the geometry. Okay. Or given the geometry, yeah. You need to know the geometry to determine polarity, because then once you identify the polar bonds, if there is polar bonds in there, and then you need to make sure that the polar bonds are they don't cancel out. If they do cancel out, then they're non-polar. If they cancel out, let me restate that. If they do not cancel, they're polar. If they cancel out, that is non-polar. The only way to determine that is through the geometry. Oh, the lone pairs, group 5, like nitrogen and phosphorus, like ammonia, NH3, or you can have pH3 or anything, bonded. Generally, you will find. Let me pull up the periodic table. There's a little bit of a bit of more information that will help you here. Okay, as I stated earlier, I said nitrogen and phosphorus. Normally, if you draw Lewis-Dot structures, you're going to end up with a lone pair, one lone pair on nitrogen and phosphorus. Try that with NH3, pH3. You'll find that. Okay. Now here's the cool thing about the periodic table, and that's why I like the Roman numerals. Everybody in group 5, we all understand that group 5 has 5 valence electrons. Okay. Also, it is it is a non-metal, so it will gain electrons. So it's going to gain 3 electrons. So we know that, right? Okay, it's got 5 valence electrons. It will gain 3 valence electrons to give us an overall -3 on as an ion. What we also know now, that everybody in group 5 will make 3 bonds. Okay. All right. Group 6. What do we know about group 6? Group 6 tells us we got 6 valence electrons. It's a non-metal. We're talking about non-metals here. It's gonna gain 2 electrons to end up with a -2 charge as it becomes ionic, as an ion, right? What that also tells us is that everybody, oxygen, sulfur, selenium, when they make bonds, they're only going to make 2 bonds, H2O, right? Think about that for a second. Let me, an example of this one, NH3, lone pair, 3 bonds of nitrogen, right? Oxygen, H2O. 2 bonds on oxygen, and plus it has 2 lone pairs. Remember we did a Lewis-Dot structure? Fluorine, group 7. Okay, it's a non-metal. It's going to gain 1 electron. When it becomes ionic, it's going to be a -1 charge, right? So up here we had -3 as an ion, -2 as an ion. Now we got -1 as an ion, right? But it also tells us that it's going to make 1 bond. And so, for example, HF, the fluoric acid, has 1 bond. But fluorine has 3 lone pairs. Always had 3 lone pairs. Okay. So nitrogen in group 5 makes 3 bonds, has 1 lone pair. Oxygen, group 6, makes 2 bonds, has 2 lone pairs, and fluorine, including chlorine and bromine and iodine, okay, group 7, makes 1 bond, H, but has 3 lone pairs. Okay. So just an observation with respect to where those elements are on the periodic table. All right. All right. Any other question? All right. Chapter 8 deals with nomenclature. Nomenclature is nothing more than name that compound, given the name, given the formula, or given the name, write the structure, or the formula, given the formula, give the name. Okay, vice versa. Now, those of you who have jumped on and done the nomenclature exam, again, as per the SAC department, chemistry department, you got to score at least an 80. So if you did an 80, you're done. You can still continue to take it if you want to improve that 80 to, to whatever value you'd be happy with. You're welcome to do that because it's set up to keep the highest grade. Now, I go in there and I do give credit. Now, the first few, sometimes spelling, the first few misspells, it's a freebie. I'll give you a freebie, okay, if you misspelled it. But after that, I don't do that because nomenclature is very specific, so you gotta be careful with the spelling. One spelling that goes wrong a lot is aluminum. Gets misspelled quite a bit, so you may want to check that. Okay. Also, the tests I did mention as an email with respect to the binary acids, HCl. When and I'm trying to get this corrected, but I go through the department. If it says HCl, if it's in solution, it's called hydrochloric acid. Okay. Like what's in your stomach is called hydrochloric acid because it's a solution. But HCl is also a gas. If it's not in solution, it's called hydrogen chloride. And I've been giving credit if you forgot to give the state of aqueous. So I give you credit for that. If you just name it HCl or you call it hydrochloric acid, give it the right name, I will give you credit, even though you counted wrong. That's because of Canvas, and I'm trying to get that corrected. What else? The other thing I sent on that module in this chapter, there's 2 other files that deal with naming these sulfate, sulfite, and the prefixes hypo. I will talk about those when we're done here. But yeah, do pull up those files and read them so you can become familiar with naming these polyoxy acids. Okay. There's a little technique you can use a periodic table to help you, and that's what those files I gave you help you with learning that technique and learning the name. Because SO4 is the sulfate, SO3 is sulfite, and you can continue to go to SO2, or you can go to SO5 and give a different name. There's a little naming sequence of steps that we can talk about to help you remember what's what. Okay, we'll talk about that after the chapter. Now, the big thing about naming compounds is we just talked about ionic compounds and covalent compounds. With respect to nomenclature, when you have an ionic compound, which we talked about now, because now you should know by now how to distinguish ionic compounds. They don't have prefixes, okay? Ionic compounds do not have prefixes. Covalent compounds do have prefixes, hence carbon dioxide, okay? An example of ionic compound like barium chloride, which would be BaCl2, it wouldn't be called barium dichloride. It's just simply barium chloride because by convention, ionic compounds are not given prefixes, just covalent. The other aspect, the periodic table. And you may want to mark up your periodic table here. With respect to metals in group 1, I've highlighted them in circle. Group 1, all the way from lithium on down. Everybody, what is it that they all have in common? All of them have 1 valence electron. All of them are metals. That means that all of them will have a +1 charge when they become ionic, okay? So you have 1, 2, 3, 4, 5, 6 elements right now to start off that 100% of the time it's charged +1 from lithium on down. Okay. Next group over, starting beryllium, group 2. Everybody in that column has 2 valence electrons. They're metals. They're going to lose those 2 valence electrons. Everybody in group 2 will have a +2 charge. That's 6 more. That's a total of 12 elements that 100% of the time what their charge will be. Okay. And then there's 4 more that I circle. Aluminum, which is number 13, always has a +3 charge. Zinc, which is right there highlighted, number 30, always has a +2 charge. Silver always has a +1 charge. And cation, CD, always has a +2 charge. Now, there's 16 elements now. I call them the sweet 16. You know 100% of the time what their charge is. What does that imply? Everybody else, all the other metals have a variable charge. They can change. For example, written in blue, copper can either be in a +2 state or a +1 charge. And how do we distinguish between that? Well, we use Roman numerals in parentheses. So when we talk about copper 2, we'll say copper parentheses Roman numeral 2. When we talk about copper 1, we'll write it out as copper parentheses Roman numeral I or 1. Okay. And that's how we distinguish those other metals as far as their charge. We don't use Roman numerals for those written in red. Okay. Because those we know 100% of the time what charge they have. There's 16 of them. Okay. Everybody else can have a variable charge from a +1 all the way up to a +6. And it depends on the reaction conditions. Okay. Now, at the other end of the spectrum, when we're talking about the monatomic ions, nitrogen, phosphorus, oxygen, all the way down here, the ones I've highlighted here. When we're talking about the ions, you know 100% of the time, if you don't, you should know, what their charge is, okay? Group 5 always have a -3. Group 6 will always have a -2, and group 7 always have a -1, okay? So right now, 1, 2, 4, 5, 6, 7, 8, 9 of the nonmetals, you know 9 charges for the nonmetals when they become ions. So right now, you can mix and match. You can hook up all the positives, all the metal ions that you have highlighted in red and put them together with the chloride, the bromide, lithium fluoride, lithium chloride, lithium bromide, lithium iodide, lithium oxide, lithium sulfide, lithium nitride, lithium phosphide. You see how that works? Go down to sodium, do the same things. So you have already access to maybe total, I don't know, ballpark 300-400 compounds that you can put together. Okay. You got aluminum chloride, aluminum fluoride, aluminum nitride, aluminum oxide, aluminum sulfide, all this mixing and matching you can do. You're going to mix and match positive and negatives only. Okay. You're not putting together 2 positives or 2 negatives. All right. So those are the 16 elements, you know, their charge when those elements become ions, specifically cations. And you know the nonmetals that become anions and their specific charge, okay? Because you'll find that, let's say you got together iron and chloride, okay? So you got iron chloride. Well, the question is, well, what is the charge on this iron? Well, I don't know, right? But what do I know? I know that the chlorides each have a -1, and there's 2 of them. And I also know that when I put these together, they're going to be equal to 0. So I got Fe -2 = 0. Because when I put them together, I got to put enough of the pluses and the negatives so they cancel out. So that tells me in this stage, in this particular example, the iron is a +2 charge. Okay, +2 charge. Because I know what the anion is. I'm going to know one or the other. I'm going to know the charge of the cation to figure out the charge of the anion, or vice versa. All right. Let's go back to the slide. All right, so naming of the atoms, we've done this quite a bit. We talked about simple naming with respect get to know at least the first 20. And then we added barium, cobalt, iodine, copper, iron, lead, mercury, um, silver, gold, zinc, stannous, by the way. If we will accept SN, stannous. You're probably familiar with this morning when you brush your teeth. You look at the box. If you open up the box and it says stannous fluoride. Well, that's what this is, stannous. Another name for tin, Tin, not Tim. Let me rewrite this. Good old fashioned tin. Okay, so we will accept for SN either stannous or tin, Tin. Either one will work. Okay. Then strontium, nickel, bromine, chrome. This is the interesting one. Manganese versus magnesium. Those two get confused quite a bit. Mn versus Mg. And then cadmium. Okay, so when the compounds, the metals become ions, their particular name, as I mentioned a long time ago, does not change. So the sodium element becomes a sodium ion. And that's true for all the other metals. We talked about ionic compounds. Ionic compounds is a combination of a metal and a non-metal. Okay. Covalent compounds are made up of nothing but non-metals. AKA another name for them is molecular compounds. Either term is fine. Now we have monatomic ions, all the metals that are just the metal itself. You got the sodium ion, the chloride ion, the calcium ion, okay? But we also have polyatomic ions. Now, go to the periodic table on the bottom left side. There's a table of the most common polyatomic ions that we're going to use, okay? Remember this, these polyatomic ions come to us in a packet. They are not separated individually. So for example, NO3, which is this one right here, okay? It has its own specific name, nitrate, okay? And its formula is NO3 with a negative charge. Now there's another one called NO2 negative, but it's one less oxygen than the nitrate. It's called nitrite. The point about these polyatomic ions is this. If I need more of them to show that I need, remember, when I put them together to write a formula, I got to put enough positive and negatives together and equal 0. So if I need more than one nitrate, then I have to put parentheses around the whole unit and put a subscript to show I got more than one. If I only need one, no parentheses is needed. I just NO3, I'm good to go. Okay, but if I need more, I got to put a parentheses around it with a subscript. These polyatomic ions, again, are units that stay together and they have their own specific name. You might be tempted to call that nitrogen oxide, NO3. That would be incorrect. That whole unit is called nitrate. Okay, nitrate. Right. So let's go back. And here we got the phosphate example, PO4 -3. The whole thing has a -3 charge. The hydroxide, OH negative, we're going to use that quite a bit for the next chapter dealing with acids and bases. And then carbonate, CO3 -2. Okay. Now, it's whether you write -2 or 2 negatives, the same thing. Doesn't make any difference. Now, we talk about oxidation state. I'm going to change from charge. Right now, we've been talking about ions. and they have a specific charge. However, when we get into covalent compounds, they don't really have a charge, but because again, covalent compounds don't have a full negative charge, full positive charge, but they do have a partial negative and a partial positive property. So to encompass both covalent compounds and ionic compounds, we use the term oxidation state, and it's just a simple fancy name for its particular charge, okay? And so everybody in group one, all the ions in group one would have an oxidation state of +1. Everybody in group 2A would have an oxidation state of +2, okay? And this talks about the 16 I gave you, group 1, group 2A, and then the 4 other elements that have a constant known oxidation state. All the other elements have a variable oxidation state. And copper can be 2 different states, a +1 or a +2. Iron, for example, could be a +3 or +3. Chrome can vary too, so they all can vary, but we need to distinguish them. We'll learn here in a second. Metals lose electrons, as we talked about, form charges, okay? We talked about this also. I overemphasize because sometimes people get lost and say, well, what charge does it have? My first question would be, what group is it in? Remember, these are for groups, the A, the main elements. So 1A, group 2A, 3A, all the way through. Okay, we know they got a +1, +2, +3 charge. Because they're metals, they're going to lose electrons, okay? And then all the other metals can vary in oxidation state from a +1 to all the way up to a +9. Can vary. So how do we distinguish those guys that we don't know 100% of the time? We use Roman numerals. And so copper could be either Roman numeral I, but here's the key to remember. It's Roman numerals with a parentheses. So copper 2 +2 is written copper and then parentheses Roman numeral 2 and parentheses. Okay. That Roman numeral applies to the metal. It doesn't apply to its corresponding anion, its partner. So if you see a Roman numeral in the name, it applies to the metal and it tells you what oxidation state that metal is in. Okay, iron 3 written as iron Roman numeral 3. Don't forget the parentheses. Lead 4, Roman numeral I4. Now, if you, and I just realized that sometimes I guess they don't teach Roman numerals as much as they used to. Okay, and so maybe I need to do something. Roman numerals are the ones we use. There's uppercase, so I is equal to 1. Okay, double I is equal to 2. 3 I's, low uppercase 3. Now, if you got an I and a V, that is equal to 4 because V is 5. And if you put the I in front of the V, you subtract 1, and she got 5. And then if you put that I after the V, guess what? You got 6. Okay. And VII, 2 I's, you got 7. And then V triple I, you got 8. Now, X is 10. So if you put an I in front of the X, guess what? You got 9. And then X, if you need it, is 10. Interesting thing about Roman numerals, and I guess, the Romans use this for their math, they have no symbol for 0. Okay, interesting, huh? Okay, so that's the Roman numerals, and that gives you the charge, what that represents. Okay, so I rehash the Roman numerals there. All right, we know about anions. These are nonmetals gaining electrons. We know group 5 will have a -3 charge. Group 6 will have a -2. Group 7 will have a -1. Chlorine always have a -1. What that means that chlorine, bromine, and iodine can not be a -1. Depends on the conditions. We'll learn more in a bit. And of course, we know group A will always have 0. Noble gases have an octet. They're happy. We're going to begin by learning formulas and then the names for the ionic compounds. Okay, remember that ionic compounds are made up of ions, and ions have a charge. The sum of the charge must be equal to 0 when we put them together. So another way to say that would be, in general terms, would be as follows. That if you say the number of cations when you put them together plus the number of anions must equal 0. Okay? A more generic formula would be, because you have some homework that they may have the overall formula is, I'm getting an unstable signal again. The heck? Okay. Instead of saying 0, we could say the charge of the compound, whatever it may be. 9 times out of 10, the charge is 0. But occasionally, could have an actual charge. Okay. So the number of cations plus the number of anions must equal the overall charge of the molecule, which 9 times out of 10 is generally 0. All right, now polyatomic ions. Here's the table. They have their own particular charge. Okay, and as I stated before, if we need to use more than one, we got to keep them together, and we put parentheses around it to show that we need more than one. Okay. When we put these together at this point in time, the compounds must be neutral / overall charge. Or if we got to add enough cations, enough anions, so they equal 0. We're going to start with that. So let's combine sodium and nitrogen. Well, the first thing we do is we convert them to ions. And I know that sodium is in group 1. And so sodium will always have a +1 charge, right? Nitrogen. When nitrogen becomes an ion, what charge does it have? What's the oxidation number of nitrogen when it becomes an ion? Okay. I just saw a message here popped up. Let me back up. You want the group lone pairs, Barbara? Did you get that? I did mention that. Okay, try to review the correct structure formula for the nomenclature, spaces, etc. Yeah. Yes. Yes, we're going to be, Claudia. We'll be doing that. And yes, Claudia, -3 is the charge for nitrogen when it becomes an ion. Not only that, its name becomes nitride. Okay, so keep that in mind as we need to name it. Okay, nitride. The metal part, name doesn't change. The non-metal part, name changes. Nitrogen becomes nitride. Nitrogen, phosphorus becomes phosphide. Oxygen becomes oxide. Sulfur becomes sulfide. Chlorine becomes fluoride. Chlorine becomes chloride. Notice the thing in common, the IDE at the end. Okay. And so we write them in formulas first, then we got to have enough of each so they cancel each other out with charges. So I need 3 sodiums to cancel out the -3 of the sodium. So that 3 in front of sodium becomes the subscript for the sodium. So its formula would be Na3 subscript 3 N. Its name would be sodium nitrite. Okay, not sodium nitrogen, but sodium nitrite. Now, what's the trend here? And the element is nitrogen. When it becomes the anion, it becomes nitride. When we hook it up with 3 oxygens, it becomes nitrate in the polyatomic ion. And when there are only 2 oxygens, it still has a negative charge, that becomes nitrite. Okay, so the 8 and the ite deal both not only for nitrogen, but with sulfur, sulfate, sulfite. When you see ite, ITE, and ATE, you're dealing with that element with the addition of oxygen bonded to form the polyatomic ions. So you have nitrogen as the element, nitrite as the ion, nitrate when that ion is hooked with nitrogen is bonded with 3 oxygens and has overall negative charge to form a polyatomic ion. And when it has 2 oxygens, it's nitrite. Okay. Same is true with sulfur becomes sulfide, and it becomes sulfate and sulfite. All right, let me clear up my mess here. So that's our formula. All right. So here we have sodium and sulfur. Step number 1, write them in ionic form. Okay, ionic form. So sodium, like we did the first one, is always a +1. Why? Group 1. Okay. Sulfur. What is the ionic charge? What's the oxidation number of sulfur? -2, exactly. Okay. And so those are the ions. Now we put them together such that charges cancel out. That means we need two sodiums, right? And the name is sodium sulfide. Okay, not sodium sulfur because the ion is sulfide. The name changes. So there's a formula, Na2S. Okay. Now you might think, well, wait a minute. What if I did? What if I had the formula? Okay, and here's the thing. Let me draw this. Be able to go in both directions here. Given the formula, give me the name. Is probably the. I should. Okay, given the name, give me the formula. Or have them in the formula, give me the name, vice versa. Double arrow those, okay? Now, what if you didn't know what the oxidation state of sulfur was? Okay, well, what is it you do know? We know that sodium is a +1. There's overall +2 there, right? Why? Because there's 2 sodiums here. That's what the subscript tells us. So we know that it's a +2 plus the sulfur equals 0. We generated a real simple algebraic equation. We could solve for S. We do that, sulfur is equal to -2. Okay. Right? Because we know we're always going to know one or the other as far as the charge, depending on where they're at on the periodic table. here we know both of them, sulfur and sulfide. But, you could have a condition, an example where you don't know one, but you know the other. You may know the cation, but not the anion, or vice versa. Okay, this one. Okay, we got magnesium, and I know it's in group 2, so magnesium is a +2 charge. Oxygen is the group 6, becomes an ion, ends up with a -2 charge. Okay, and so also its name goes from oxygen to oxide. Okay. And so we got to put them together, and fortunately they're both equal in oxidation number, so it's a real simple 1-to-1. Okay, I can just simply just put them together, and that is the formula. Its name would be magnesium oxide. Okay, now the term oxide stays the same whether we're dealing with ionic compounds or covalent compounds, because what is the name of CO2? Carbon dioxide. Oxide. See the name, even though it's bonded covalently, the name of the non-central atom changes. Okay. In this case, carbon is the central atom, so that would be carbon dioxide or carbon monoxide if it's one oxygen. Okay, we have potassium and phosphorus. What do we know about the charge of potassium, the oxidation state of potassium? Well, find it in a periodic table. It's in group 1, right? So it's going to be a positive charge. What about phosphorus? What is the oxidation state of the ion of phosphorus, which becomes phosphide? Exactly, -3. So that, putting them in ion form first, it tells me, okay, how many of each I need? So I need 3 potassium to cancel out the -3 of the phosphide. So now I can write it as K subscript 3 P. And its name will be potassium phosphide, not potassium phosphorus, but potassium phosphide. Okay, this is a little bit of a challenge, but break it down. A lot of these problems I always talk about, break it down to the units that you know. Okay, what do we know about calcium? What is the oxidation number of the calcium ion? +2. It's in group 2. What about nitrogen? -3. All right. Now, you say, oh, wait a minute here. I got a +2 and a -3. How am I going to put this together when I don't have anything of equal? I have no reference point here. Well, I refer you to this problem. What do you do if I want to add 1/2 plus 1/3? How do I add those two fractions? What is it that I need to find in order for me to add those two fractions? And you can't Google it. Yeah, okay. You need a common denominator, exactly. A common denominator for 1/2 plus 1/3 is 6, right? So I convert the half to 6 and the third to 6. Well, this is very similar, okay? I need a common factor here. And the common factor would be what? Normally in denominator, in small fractions, I just multiply the denominators, right? I get my common factor of 6. Well, I do the same thing with the charges. So I have a common factor of 6. So I need 3 plus 2's, and guess what? 2 negatives threes. Doesn't that give me an overall common factor? It sure does. Because now that 3 becomes calcium 3 and the nitrite, I need 2 nitrites. So the formula is Ca3N2. Okay. That gives me a total of -6 for the nitrites and a total of +6 for the calcium. I got to add them together such that the charges cancel each other out when I put them together. So our formula is Ca3N2. Okay. Now, if you didn't pick up on this, check this out. You didn't hear it here, but I'm going to tell you anyway. It's a tool. Oh, what did I do wrong here? Does not the charge of the anion become the subscript of the cation? Does not the charge of the cation become the subscript of the anion? Yep. Food for thought. Okay. You know, I would say 99.999%, you know, nothing is ever 100%. even in mathematics. So food for thought. It might help you out a little bit. But if you don't see that, don't, you know, go with the common factor. Okay, you got a common number, like you do for adding fractions. All right, so we have aluminum and the chlorides. And so again, write the ions first. Aluminum is a +3 because it's in group 3, okay? And the chlorides are -1, they're in group 7. That means I need 3 chlorides to balance out the oxidation state of the +3 of the chlorides, of the aluminum, excuse me. So our formula is AlCl3, okay? And now we got zinc, which is a +2, and iodide, which is a -1. So I need 2 iodides. It should be, so up here we have sodium sulfide, magnesium oxide, potassium phosphide, okay, calcium nitride, aluminum chloride, zinc, zinc iodide. Okay, notice the anion name changes. Sulfur went to sulfide, oxygen went to oxide, phosphorus to phosphide, etc. Okay, the metal name remained. Also notice something, we did not use any Roman numerals here. Why is that? Because all the metals here are part of the sweet 16. They have a known 100% of the time oxidation state. Okay. Yes, haven't done any variable charges yet, but will be. So right now, the sodium's group 1, magnesium group 2, potassium group 1, calcium group 2, aluminum is part of the 16, and the zinc is part of the 16. So no Roman numerals here with respect to the name, because all these metals only have one oxidation state. It's not variable. Okay. And so we're 5N and 8 instead of IDE. Where, oh yeah, Skylar, yeah, Skylar answered it right there. The ATE only deals with the non-metal that's attached to oxygen. So NO3 would be nitrate. SO4 would be sulfate. Okay, refer to the polyatomic table. And I think we got one more here. All right, now we got a polyoxidation, as you may restate that, and a metal that has a variable oxidation number. And we got Cu, which is copper, Roman numeral 2, which tells you, okay, its oxidation state. And without that information, you don't know unless you're told. So you are dealing here with copper plus 2 because of the Roman numeral. And we know that oxygen is a -2, okay, because it's in group 6, right? And it becomes oxide. So fortunately here, it's a simple 1-to-1, right? You've got a +2 and a -2. I can simply put them together as a 1-to-1 ratio, and that is our formula. Our name, however, would be copper 2 oxide. Now, somebody asked a question about the spacing. There's not a problem with respect to copper space and Roman numeral 2. Well, and then with space, no space. I've gone through most of. I'm still going through them. Most of the answers in the canvas, and if you write it with no space and you get discounted or not given credit, let me know. I will get it fixed, because me, it's no difference whether you put a space after, before the parentheses, but do make sure you got parentheses. The parentheses is necessary. So beginning parentheses, Roman numeral 2, and parentheses. Also make sure they're uppercase Roman numerals, okay? Yes, you'll be able to see that. Your answers are shown if you got that wrong. And what I do is once you are, if you took the nomenclature exam, you got less than 80, I go in there automatically and I check. And I check for myself to make sure you got the proper credit. Okay. But if I miss it, shoot me an email, tell me, please tell me which one, what number, and I'll go in there and fix it. All right. Speaking of copper, I used to, growing up in Superior as a kid, I used to play in this little lagoon that had beautiful, beautiful blue water. As a kid, I thought it was ocean water. I'm like, wow, this is cool. Didn't know what it was until later on the road. It was a copper ion solution, and a lot of times they use a cyanide compound to extract copper. So we're playing all these heavy metals there. I wonder if still kicking, given what we played with as a kid. All right, so let's move on. Oh, here we go again. We have lead, PP, Roman numeral IV, which is 4. So therefore we are working with, okay, lead with a +4 charge. And we know that the oxygen is a -2 charge. So therefore we need 2 oxides per 1 lead ion, okay? And that gives us the formula. And the name would be lead, Roman numeral 4, oxide. All right. Now, when you're putting these together, okay, remember that Roman numeral is the oxidation state of the metal. And it has nothing to do with how many of those ions you have, because I've seen people put in Pb4 oxygen. That's not correct. Okay, so that Roman numeral deals, again, I repeat, with the oxidation state of the metal, which then you can determine based on the anion how many of whatever you need to put together. Okay. The other aspect is I lost it. Yeah, it'll come to me. All right, so make sure that if you're given a formula and you see it's a negative, well, make sure it's equal to 0. However, that's why I gave you the general formula that it's not necessarily 0. You could have a polyatomic ion, for example. Let's take one. Let's do an example. All right. We have sulfate, which is SO4 negative 2. All right. Question is, what is the oxidation state of sulfur in this state? Now, the fact that it is bonded, it's a central atom. If this was just sulfur by itself, no question, negative 2, but it's bonded to oxygen. So it has a totally different oxidation state. In fact, it's going to have a positive oxidation state because it's bonded to oxygen. And so what do we do with the general formula? Is, well, what do we know about oxygen? Oxygen has a negative 2, each one, right? The oxide. So we can write sulfur plus negative 2 times 4, because there's 4 oxygens, and the overall charge is the negative 2. So we have sulfur minus 8 is equal to negative 2. We got sulfur is equal to negative 2 plus 8, okay, which is equal to plus 6. And so you can see in this state, sulfate, the sulfur has an oxidation state of a plus 6. And I use that general formula of number of cations plus number of anions, okay, is equal to the overall charge of the molecule, which 9 times out of 10 is 0, but you can have an example where it's not. It could be, negative 2 in this case, okay? All right. Now, with respect to polyatomic ions, here we have magnesium, and then they give you OH negative. That should be a flag to tell you, let me go to the polyatomic ion table, because they're giving you the charge of this polyatomic ion, okay? And that, by going to the table, it's also going to give you the name for that polyatomic ion. But we put it together like we do the others. We got magnesium, we find its oxidation state as an ion, it's a +2. The polyatomic ion, the hydroxide, is a -1 for the whole unit. That means we need 2 of them. We need 2 of these units. If you ever take Tums, that's what you're drinking, the hydroxide. Or milk of magnesia. You're drinking the hydroxide, because we're going to learn that hydroxides react with another species to neutralize the acid. So we need 2 hydroxides and 1 magnesium. And since this is a polyatomic ion, that means that we're going to use a parentheses, because we need more than 1. We need a parentheses to designate more than 1. And so we put it as follows. So this is magnesium hydroxide would be the name. Okay. All right, PO4 negative 1. Again, you see phosphorus, you might think phosphide, but there's oxygen right behind it, and there's 4 of them. And that whole thing has a negative 3 charge. So that sends you to the polyatomic ion table. Search for that, and you see PO4 is called phosphate. Potassium has a +1. We need 3 of them. And so our formula becomes K3. Now we don't put a parenthesis around PO4 because we only need 1. Okay. So this is called potassium phosphate. You'll find that a lot in all kinds of foods and preservatives and so forth. Check your labels. Let's see. All right, here's SO4 negative 2, another polyatomic ion. Okay. What do we know about silver? Silver is one of the sweet 16 and always has a +1. Okay, so silver has a +1. We need 2 of them. So our formula becomes Ag2SO4. We need 2 because sulfate is a -2. So far we got magnesium hydroxide, potassium phosphate, and now we have silver sulfate. Now we got calcium and the NO3 negative. Polyatomic ion table tells us that is called nitrate. Okay, nitrate. And we got calcium, which has +2. Okay. And nitrate has a -1, so that means we need more than 1 nitrate. So we use a parenthesis to show we need 2 of them. It will be 100% incorrect to do this. Say calcium N2O6, thinking I need 2, so I could add just, no, that would be 100% incorrect because don't know what N2O6 is. It's some species of something, but it's certainly not nitrate, which is what we're dealing with here. Okay. So whenever you need more than 1 of the polyatomic ions, you always use parentheses. And then the subscript of the outside the parentheses tells you how many of those units you need. Let me clear this up a little bit. Here, copper 2, Roman numeral 2. Again, that Roman numeral belongs to the copper, so its charge is a +2. So we got a +2, and then the CO3 is carbonate. Okay, find that on the periodic on the polyatomic ion table. Carbonate. Let me direct you to that just to refresh your memory. Right here on the far left of the periodic table. Here's the carbonate we're just dealing with, called carbonate. Here's its name. Okay, and then hydrogen carbonate or bicarbonate. You're familiar with bicarbonate. You may put that in your chocolate chip cookies. Okay, and so forth. So you notice that you have only 1 anion, negative charge. There's only 1 cation, polyatomic ion, that we're going to be using, and that is the ammonium. That is ammonia with an extra hydrogen, NH4 negative +1. Okay, but most all of them, the anion is a negative charge species. And so it's a simple, straightforward 1-to-1. And so we have here, I'll start from the top again. The name is magnesium hydroxide. Number 2 is potassium phosphate. Silver sulfate for number 3. Calcium nitrate for number 4. And now we have copper, Roman numeral 2, carbonate. Okay. So remember to use the parentheses when you need to use more than 1 polyatomic ion. Right. We learn some names. Names depends on how they're fixed. So we're going to work backwards. So remember, as I mentioned, we got the formula NaCl. Okay, you might be tempted to call it chlorine, but keep in mind it's not diatomic. There's no 2 there to think that maybe it's the element. Also, you always have, notice with ionic compounds, the metal is always displayed first. So sodium, you wouldn't, by convention, you would not see it chlorine, then sodium. It will be the metal, like the name, sodium chloride, potassium chloride, magnesium chloride, etc. Okay. I talked at length already about the anion and the name change, so chlorine becomes chloride. Okay. How about this one? What do you think this would be? ABr. Potassium bromide. Oh, that would be correct. Potassium bromide. How about MgO? Mg, which, if you know, is magnesium, and then O is oxide, exactly. And then we have calcium, and then Fl2. You might be tempted to think, oh, diatomic fluorine, right? No, the fact that you got metal first, the calcium, and then the F2 tells you that this is an anionic compound. So it's calcium fluoride. Notice, why don't we, for the first 3, why haven't we used Roman numerals up to this point for the first 3? Exactly. It has the fixed oxidation number, okay? And the charge would be okay, you can use that. But I'll be using oxidation number because we're going to get into covalent compounds that don't really have a charge. All right, then we got lithium sulfide, okay? And then we got silver chloride, silver chloride. And then the important part is this: ionic compounds. All ionic compounds do not have prefixes. Okay, and so for number 3, it's simply calcium fluoride and not calcium difluoride. Okay? Now you might find it on labels. I see that a lot, and I just cringe when I see the naming. I don't know if it's marketing or what, but sometimes on labels, if you have you have ionic compounds, they put prefixes, which is totally incorrect. Keep in mind, this naming business is not something we here made up. This is set worldwide. There's an organization worldwide that looks at the compounds, and everybody agrees that these are the names of the compounds. That is, therefore, I could be talking to a scientist on the other side of the world and just giving them the formula. They know exactly what we're talking about. I was once in the lab, we were trying to make a compound. I had myself, a guy from Lebanon, a Japanese scientist, and I forget one from China. Our languages, each other's languages were not the best, but we just sat there and wrote on the board what we were doing, and we all understood how we're going to proceed with making this compound. So it's a language, okay? Now, polyatomic ions don't change the name. They have their own name. So it is this one, NaNO3. It is nitrate. It would be incorrect to call that nitrogen oxide. That is not the correct name. Okay, so here we have K3PO4. Okay. Now you might say, well, how do I know it's polyatomic ion? Well, the first thing is this: you see that the metal's written first, so you know potassium, whatever, or whatever metals there is, and then you see the non-metal come up. Now, in this case, it's phosphorus. You might think phosphide, but immediately following that first non-metal, you find oxygen. Okay, so you might be tempted to say phosphide, but immediately following that, you have an oxygen. So that should be a flag to say, I got a polyatomic ion. Let me go to the polyatomic ion table, see if I can find this. And yes, Skylar, that would be correct. This would be potassium phosphate. Okay. It'd be the same would be true if it was written with this. Okay, we got potassium, and then you see sulfur. You might think potassium sulfide, but then immediately next to it, you got oxygen. So that should tell you flag polyatomic ion. Go to the table, guess what? That is sulfate. So you see, we're building up on your whole database of compounds. You're probably up to 500-600 compound names right now. You're playing with all the metals that you can think of, all the anions and all the cations. You know, you can mix and match, you know, and make up all kinds of compounds. All right, potassium phosphate, and here we have flag for you will be the parentheses. All right, notice the first one didn't have the parentheses, so I used the thought, I'll get the single phosphorus, move over, I got oxygen. Here, no question about it, I got parentheses. Go directly to the, if you don't know that name, go directly to the polyatomic ion table on the periodic table, and you have calcium hydroxide, aka TUMS. Okay, calcium hydroxide. Then we have, again, similar situation. We got zinc and then the S, but followed by oxygen sulfate on the polyatomic ion table. So we got zinc sulfate. Okay. Again, no Roman numerals. Again, why? Because these are fixed, known 100% of the time charges. They're not variable oxidation numbers. Okay. Given this, okay, what is the name here? So we'll break it down. Earlier, I said you may not know what the oxidation state is of one or the other, but you're always going to know one or the other. Okay, so what do I mean by that? Well, let's take a look at this one. We have copper Cl2. We don't know what the oxidation state is here. So, but we got to figure it out. And what do we know? We know that the chlorides each have a -1, and there's 2 of them. So that means that we have Cl plus a -2 equals 0, because that's the overall charge of the molecule. So we generated an algebraic equation. Copper plus -2 equals 0. We solve for copper. Copper is a +2, okay? Which tells me that name-wise, I'm using Roman numeral 2. So therefore, the name here would be copper, Roman numeral 2, chloride, excuse me. I was thinking oxygen. Chloride, okay? Copper 2, Roman numeral 2, chloride. All right, let's do this one. We have lead, but each oxygen is a -2, right? And we got 2 of them. And so I got 2 times a -2, and overall the charge is 0, so it's equal to 0. And so I got PB -4 is equal to 0, I should say. So PB is equal to +4. And so what we have here is lead, Roman numeral 4, oxide. And see how we work that. Right now, we don't know what the metal part is, but you could be in a situation where you know the metal part, but you don't know the anion part. You know the cation part, but not the anion. Right now, we don't know what the cation is, but we know the anion. All right, so that, let me turn this up a little bit. Lead, Roman numeral 4 oxide. Okay, what about this? We know the parent name is nickel, and we know we got bromide, right? Oh, nickel 3 bromide. How do I know that? Because I know that each bromide has a -1, and there's 3 of them because of subscript 3. So that means I got a total of -3 charge, which tells me the nickel must be a +3. Therefore, this is nickel, Roman numeral 3, bromide. Okay. The sulfate, SO4, is a polyatomic ion. Okay. We're not going to use a lot of polyatomic ions. There's a lot of them, but basically, just sticking to the table that we utilize, we're going to be using basically that one. There is for the nomenclature exam, I did send an email, and that was a carbide. Carbide's a special case. I sent an email, but I want to reemphasize that it's an anion. There's actually 2 carbons, and it has an overall charge of a -2. This is the carbide coming from carbon. Okay, carbon is very unique. It can be gain 4, lose 4, because it's on the fence. So just keep this in mind. Carbide, its form is C subscript 2, but it has an overall charge of -2. Another, no, I'll come back to that. So we got the sulfate here, and it's sulfate is a -2 because if you look that up in the polyatomic table, it has an overall -2, which means the manganese must be in the oxidation state of a +2. Hence, we use a Roman numeral 2. Don't confuse Mn for Mg, magnesium versus manganese. That can be very confusing at times. All right, we have Cu, which is copper, and then we have NO3, which is nitrate. Nitrate, if you look at the polyatomic table, has a -1 charge. That means that this copper must be a +1 charge. So it has Roman numeral 1. Okay. Keep in mind, it's important we use Roman numerals here because there's also a copper 2 nitrate species. Okay. And there's also a copper 2 oxide or a copper 1 oxide. Notice here that you can do all mix. We can mix and match. You got the lead, hook it up with the bromide, take the lead, hook it up with the sulfate, lead with the nitrate, do the same with the nickel and oxide, nickel and sulfate, nickel and nitrate, do all these combinations. You can have a variety of different compounds now. You're probably up to about 1,000 different compounds now that you can put together. And then finally, we have CO, which is cobalt, and then we have N, and it's simply N. I look next to it, there's no oxygen. So what we're dealing with is nitride, okay? Note compared to number 4, you see nitrogen sitting there, but right next to it, on the right-hand side is oxygen. So that's the polyatomic ion. Here we have nitride. And nitride is a -3. So that means that cobalt must be a +3. So therefore, its name is cobalt Roman numeral 3 nitride. Okay. And again, I can mix the cobalt with the oxide, the bromide, the sulfide, the sulfite, the nitrate, the nitrite. And I'm just building up a database of a whole bunch of compounds. All right, here we go. What do you think the name of this species will be? Well, we got something in parentheses that should direct you to the polyatomic ion table, and you'll find it to be carbonate. Okay, and the carbonate has three of them. There's three of those carbonates. Each one has a -2 charge. So that means that iron, what kind of oxidation number does iron have here? Okay. The the carbonate has a -2. Okay. The parentheses tells me I got a polyatomic ion. I go to the table, I find it CO3 -2. Okay. The subscript tells me there's three of them. So I got a total of -6 for the three carbonates. All right. I have two irons plus I got a -6 for all the carbonates, and that equals 0. What must be the charge on each iron? A +3, and that is correct. Okay, so I can go 2Fe, my little algebraic equation, okay, and divide by 2 here. So Fe is equal to a +3. And it makes sense if you think about it, right? Since there's each carbonate is a -2, and there's three of them, it's a total -6. That means that each iron must be a +3. Okay, to counter the total -3 of the carbonate. And so our name is iron, Roman numeral 3, carbonate. And again, here we can do all kinds of mix and match. All right, here we have number 1, SR is strontium, okay? And the OH is a hydroxide, the polyatomic ion. So its formula is SR. We need a parentheses for the hydroxides because we need 2 of them. Strontium is in group 2. Being in group 2, it's a metal, it will have a +2 charge. So that means I need 2 negative hydroxides to counter the +2. Okay. Strontium is number 38 on the table. AuCl3, we just need the name here. We don't know what the oxidation state is for gold, but we do know the oxidation state for the chlorides. Each one is a -1. Where there's 3 of them, that means the gold must be a +3. And so its name will be gold, Roman numeral 3, chloride. The zinc is a +2. The oxide is a -2. Straightforward. 1 zinc, 1 oxide. Its name will be simply zinc oxide. Okay. The barium, this was a little more challenging, but again, we're looking, as we did before, the barium has a +2 charge. Why? It's in group 2, it's a metal. The phosphates that given to you there has a -3. It's one of the polyatomic ions. So we got a +2 and a -3. Okay, we find a common value, which is 6. Okay, that means that I need 3 bariums and 2 phosphates. So the formula is given there in number 4. We got Ba3 right here, and parentheses because we need 2 phosphates. Okay. Again, think about it. the charge of the anion became the subscript of the cation, and vice versa for the subscript of the anion. All right, then we have SO3. You might be tempted to call that sulfate, but be aware in your polyatomic ion, you got SO3 and SO4. Okay, and the SO4 is the sulfate, and the SO3 is the sulfite. Lithium is a group 1 metal, so it has a +1 charge. Let me clear this up a little bit. It's a +1 for lithium because it's in group 1, so I need 2 lithiums for every sulfite. So I got number 5, Li subscript 2 SO4, or otherwise known as lithium sulfite. Aluminum is a +3, and sulfur becomes sulfide with a -2. So again, we have the similar charges, oxidation numbers. So we find a common factor, which again, in this case is 6. And so we need 2 aluminums and 3 sulfides to balance the overall -6 and +6 charge. And the formula is Al2S3, otherwise known as aluminum sulfide. And then finally, they just need in the name of this one. We got a parentheses, okay, that should send you to the polyatomic ion. Each of the nitrates have a -1, and there's 2 of them. That means that copper must be a +2. Therefore, its name will be copper Roman numeral 2 nitrate. Okay. And again, you can do a lot of mix and match here. Strontium chloride, you can, mix up the strontium with the chloride or the oxide or the phosphate or the sulfite or the sulfide or the nitrite. Okay, and then vice versa, take the gold with the hydroxide, gold with the oxide, et cetera, et cetera. So your database of compounds is slowly being built up. Okay. Okay. Here they just want you to give the formula. And so, but what is recommended when you're given the name is to first write the ions. Okay. So you got sodium nitrite. And so you look up sodium, sodium is a +1. And the nitrites, notice the ITE is a -1. It's 2 oxygens, NO2. Okay. And so I can very quickly put it together with 1 sodium and 1 nitrite, because each one's a +1 and a -1 respectively. Nickel, Roman number 3, that tells me that I'm using nickel +3, and the oxygen is a -2. Okay, so write them in ions first. Magnesium is a +2 oxidation state. Iodine is a -1. It's in group 1. I'm going to need 2 of those. Aluminum is a +3. Cyanide. Cyanide. Go to polyatomic ion. You will find it to be a -1. That's a CN -1. So when you're given a name, put everything in ions first so that you know how many of each you need to put together. And so I need 2 nickels and 3 oxides. I need 2 iodides, and I need 3 cyanides here. Okay. And what that does, it gives me the following formulas. Here, I'm messing. Okay. All right. So, given the formula, put them in ions first, and then combine them with the appropriate number of each to make sure they balance each other out to equal 0 for these examples here. Okay. Now, the key points to take away from here is one, I gave you 16 elements that have a fixed oxidation number. Okay. Those 16, we don't use Roman numerals to distinguish. There's only one of those ions. That means that all the other metals have a variable oxidation number. Okay. Therefore, we have to use Roman numerals for all the other metals. The anion part, the nonmetal part, their name gets changed. Sulfur becomes sulfide, oxygen becomes oxide, etc. Then we have polyatomic ions that we utilize. Okay, remember to keep those together in units. And if we need to use more than one, then you put a parenthesis around it and put a subscript to give you more than one. Okay, those are the main points with respect to ionic compounds. Again, these are ionic compounds. This is a combination of a metal and a nonmetal. Okay, notice number 4, aluminum cyanide. The nonmetal is a cyanide made up of carbon and nitrogen. Polyatomic ion, but nevertheless a nonmetal. Aluminum obviously is the metal. So these are ionic compounds. No prefixes here. No prefixes in ionic compounds. So number 3 or number 2 would now be called dinickel trioxide. It'd just be called nickel Roman numeral 3 oxide. And that Roman numeral has to deal with the oxidation state of the metal. It has nothing to do with how many of those metals you have. Okay. All right. When it comes to covalent, or AKA molecular compounds, again, made up of nothing but nonmetal combinations. Okay, so they're not ions, but they have an oxidation number. Okay, and we use prefixes. Now we use the prefix for 1, mono, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 9, nana, N-O-N-A for 9, I should say, and deca for 10. Okay, if we need it. How do we do it? Well, we use basically just like this. We got the first one, the first one written down is the central atom, and everything following that is bonded around the central atom. Like ionic compounds, what's always written first is the metal. In this case here, for molecular compounds, the first one, first nonmetal, is the central atom, then it would be followed with whatever's bonded around it. If there's more than one of the central atoms, we use a prefix, okay? And then its metal name, we don't change the name. So if it is carbon, it's simply called carbon. Now, what follows is the whatever's bonded to the central atom. And here, we change its name like we did with ionic compounds, and we take off the suffix and give it the IDE. So oxygen remains as oxide. Fluorine becomes fluoride, etc., etc. And here we also put a prefix to name how many of the second atom are there. Okay. And if there's the first nonmetal is just single, we just simply say whatever it is. For example, if the second one is by itself, we have to use the term, the prefix mono. Let me give you an example. We have CO versus C double O. This one is, you may not know, is carbon monoxide. Okay, notice we use the prefix mono to designate one oxygen, compared to the second one, which is called carbon dioxide. Okay, we use the prefix di to designate 2. There's di, okay, and mono. And so the second nonmetal, if it's by itself, we have to incorporate the word monoxide. Technically, hydrogen, H2O, its name would be called dihydrogen monoxide. That would be water. In fact, you can Google that. You'd be surprised at the crazy stuff that comes up. If you look up at the health hazards of dihydrogen monoxide, you'll come up with a lot of crazy stuff. All right, maybe the best thing to do is it's deadly stuff, especially if you can't swim. Can be deadly. Okay, so let's move on to this one here. So we know this is pretty common. Carbon. We got two oxygens. Oxygens become oxide. There's two of them, so it becomes dioxide. Okay. So I use that example. Carbon, only one oxygen. So the parent name is, this is when it comes to these type of molecules, covalent compounds, what I do is I first write the parent name. I forget the prefixes for right now. I know the first one's called carbon, and I know the second one is oxide. Okay, but then I look at the numbers. So I know that there's a 2, so that becomes dioxide, right? Well, I do the same thing here. I got carbon and then oxide. That is the parent name. Now I look at the prefixes as far as the numbers. There's only one oxygen, so obviously this becomes monoxide. Okay. Notice I wouldn't say monoxide. It's an English kind of thing because a lot of these prefixes end in the vowel, and if your oxide and your other letter has a vowel, you got to drop one of them. So you drop one of the O's, drop the O from the O. From the mono, you drop the O from the oxide. So either way is monoxide. So it wouldn't be two O's back to back. All right. Now, here's one. First step, write the parent name. So I got phosphorus. That doesn't change as the first species. And guess what? I got the oxide again. Okay. So that's my parent base name. Now I go back to see if there's more than one. There's 2 phosphorus. So guess what? That becomes di. And then there's 5 oxygens, and the prefix is penta. Now, here's a vowel, which is A, and a vowel, which is O for oxide. We're supposed to drop the A from penta, and that becomes pentoxide. Okay. If you forget to do that, I'm not going to make a big deal out of it. And if it looks like that, all right, I'll take it. No big deal. But technically, that A should be dropped, pentoxide. I know if this was an English class or English teacher, I'll mark it off. All right, so now we have phosphorus and chlorine, which is fluoride. Okay. And so I write, like I did earlier, write the parent name, phosphorus, and fluoride. Okay. Now I go back and look. It's only one phosphorus, so I don't need to put a mono. It's only the second after the central. Just leave phosphorus alone. Okay. But there's 3 fluorides, so it becomes trifluoride. So that name is phosphorus trifluoride. Okay. Next one. Parent name again. I is first. That means that iodine is the central atom, so it doesn't change its name. So it's iodine. The name stays like its elemental name is. And then that's fluoride. And there's 7 of them. So heptafluoride. So I write in the hepta fluoride. Notice I didn't drop the A. because the F is not a vowel. So heptafluoride. And then finally, oh, and that's it. So here, again, when you're given the formula, write the parent name and then go back and add the prefixes. Also, we can determine the oxidation state from the central atom. If you look at carbon, number 1, what do you think the oxidation state is for carbon monoxide? The carbon is, could you calculate that? What is the oxidation state of carbon in carbon monoxide? Okay, what do we know about the oxide? It's a -2. What does that imply? This carbon must be a +2. Yeah, but no, in this state, yes, carbon could be a +4 or -4, depending on the reaction conditions. In this condition, the oxidation state of carbon in carbon monoxide is a +2. In this condition, carbon dioxide, this carbon is a +4. Okay. And so on. The iodine, number 4, it is a +7. Fluorides each are -1. Okay. So you can still determine the oxidation state even of these crazy looking compounds, because you know one over the other. You're always going to know either cation or anion. Since these nonmetals of the central atom, generally that's the one you don't know. It is the other part, the partner part, that you will know its oxidation state. So you can calculate the central atom's oxidation state. All right. How about this one? Br308. What would be its name? I think we're gonna run through this real quick. We're gonna be anybody take a shot at? Well, first of all, write its parent name. Okay. Odette, you got it right. Okay. The English teacher will take off the A, take a point off for the A, but that's okay. I'll accept the A after the T. And so to rehash, you're given the formula, write the name, write the parent name first, which is bromine, and then oxide. Okay, that's the parent name. And then you throw in the prefix or the subscripts, and like Odette has, there's 3 for the bromine, and octa for the oxygens or the oxides. Now keep it in mind, O is a vowel, A is a vowel. You're supposed to drop the A, so octoxide. But I'll take it with the A, no problem. All right. Here we got similar situation. Write the parent name first. So it'll be phosphorus, and then sulfur becomes sulfide. So it's phosphorus sulfide. And then now throw in the number of each. 4 would be, what would be its name? Who wants to take a shot of that one? Phosphorus sulfide. Tetraphosphorus heptasulfide. That is correct. Okay. And then this one, sulfur trioxide. Okay, you got sulfur, only one of them. You got 3 oxygens. So it's 3 oxides, sulfur trioxide. Smelly gas coming out of most vehicles, some vehicles. And then finally, iodine hexafluoride. Again, this time you're given the name. Now, no, break it down, reverse it, write down the parent formula first. I got iodine, right? And the fluoride. And that's correct, Skylar. Hexa gives me 6. So that would be the formula. Okay. and then dichlorine pentoxide. So that would be chlorine, Cl, and then oxide. That is correct. Cl2O5. And believe it or not, one last one here. In this case, we want the name. Parent name will be phosphorus and iodide, diphosphorus, tetraiodide. Again, it's a tongue twister because if you drop the A, then you got tetraiodide. There you go. All right. Just a few reminders and we'll be done with chapter here and then we can call it a day. Prefixes only for the covalent compounds. Again, no prefixes for ionic compounds, okay? Roman numerals, only for those metals that have variable oxidation numbers. Okay, so that means, again, if you forget, it's the 16, group 1, group 2, aluminum, zinc, silver, and cadmium. So you got 12 coming in from group 1 and group 2, and then 4 coming in from the ones I gave you. Those have fixed oxidation numbers and therefore do not require Roman numerals. Okay, it would be incorrect to put Roman numerals in them. Okay, so don't put them in. They're fixed. That means everybody has a variable oxidation number. Okay, polyatomic ions from the table, we don't change it. So nitrate is NO3. Don't change it to nitrogen trioxide. I've seen that happen. Don't do that. It's just nitrate. And you have that polyatomic ion table with you. So you shouldn't have to change it because it's there. And you got it there with you. Of course, you use it during your exams. Okay, so try these at home. If you want BaCl2, barium chloride, okay, nitrogen dioxide, and then we got iron 2 phosphate, and then we've got diiodine, tetroxide, silver sulfate, nickel sulfide. Okay, try those at home. I know I gave you the answers, but here, write those down if you want, and see if you can knock them out. All right. Don't forget the worksheet. It's on the course web sheet that really help. What I'm going to do Thursday is I will go over the 2 other additional papers that are module 8 that deal with polyoxy ions and the naming, the sulfate, the sulfite, and the hypo and the per. I'll go through that. If you haven't, take a look at them. They're pretty self-explanatory. They can be familiar with it, and I'll go over it quickly on Thursday. Okay. All right.